Hello and welcome to the presentation of our sensor modeling topic. My name is Sebastian Schober. I'm currently a PhD student at Infineon Technologies in Munich and at the Johannes Kepler University in Linz, Austria. And now I would like to present to you the research topic that I was working on with my colleagues. So the topic of the presentation is towards drift modeling of graphene-based gas sensors using stochastic simulation techniques. Electrochemical gas sensors are a very promising technology for tracking air quality and also for other applications. However, the long-term stability of these sensors is a big problem, also for graphene-based electrochemical gas sensors that were studied here in particular. The stability issue basically means a drifting behavior of the sensor, as it is shown in the figure here. In blue, we have a sensor signal due to concentration exposure without drift, where the signal goes up nicely to the baseline after each concentration pulse. If we now add some nonlinear drift, we get the signal in red, where this baseline steadily decreases over time, which worsens the prediction behavior of our sensor. In order to develop algorithms to address this drift problem, it would be highly beneficial to have long-term simulation data to evaluate these algorithms on. Therefore, we investigated such a model, which I would like to present now in detail. So, graphene-based electrochemical gas sensors evaluate the electrical properties of the graphene material to classify gases or to determine their concentrations. If there are gas molecules present, such as NO2 or ozone, they can adsorb onto the surface and change the resistivity or the conductivity of the material. They also desorb from the surface eventually, which can also be enhanced by using heating methods on the material. The resistance changes can then be used to determine the gas concentrations. In the model, we want to transfer the graphene grid structure of the two-dimensional graphene grid that is shown in the top of the slide to a two-dimensional grid on which we sample the adsorption and the desorption behavior of different gas concentrations to simulate the sensor signal, which is shown on the lower part of the slide. This process is described mathematically by a so-called microscopic model. Here, the adsorption process is simulated with a Markov chain, which is shown in the middle of the slide. At each time step, there is a certain probability for an empty site to be occupied by a gas molecule, in this case either ozone or NO2, and for molecules that are already occupying a sensor site to desorb. The probabilities are described by the equations on the left, where the adsorption is dependent on the gas concentrations as well as the adsorption rate. The desorption process depends on the desorption rate, the temperature, since we also simulate heat pulsing, and the energy of the binding site. The outcome of this microscopic model is the so-called adsorption fraction, which is shown on the right of the slide, which describes how many of the adsorption sites are occupied at a certain time step relatively to the total amount of binding sites. The figure on the lower part of the slide shows one step of the simulation. So it's basically a simulation snapshot, so to speak, where the blue dots represent NO2 molecules on the sensor and the red dots represent ozone molecules on the sensor. On the upper right of the figure, the adsorption fraction is shown over several time steps, and the according gas concentrations are shown on the lower right, which is basically the input of the sensor model. The advantage of this microscopic model is the possibility to implement microscopic effects that might be responsible for certain drift behaviors. There are three effects that have been implemented. On the one hand, a very well-known effect is slow sensor recovery, which means that the molecules desorb from the sensor surface much slower than they adsorb on it, which means that it takes a considerate amount of time until the sensor recovers, which leads to a downwards drift. A second possible effect for downwards drift is secondary layer adsorption. This models the adsorption in deeper layers under the surface of the graphene layer, for example at overlapping graphene flakes with a second Markov chain, similar to the surface process. An effect causing an upwards drift, for instance, would be ozone oxidation, which describes the chemisorption of an adsorbed ozone molecule, which might lead to epoxide groups on the sensor surface, which affects resistivity. Therefore, a third Markov process is introduced to sample this effect as well. So the microscopic model simulates the occupancy status of the sensor surface. This then, of course, has to be translated to an electrical signal, which is a relative resistivity in this case, by using the so-called macroscopic model. This model is based on an equation for determining the resistivity with respect to the electron and hole densities and their according mobilities. It was assumed that for clean air, the contribution to relative resistivity is constant, and that we just need to use the adsorption fractions of the main grid and the additional effects with certain scaling factors alpha in order to get the overall relative resistivity. Of course, this could also be extended by a temperature and relative humidity dependency to take such effects into account as well. For the evaluation of the model, we first did a simulation study on the impact of the different drift-related microscopic effects in order to determine if these effects cause the expected drift behavior. The simulation involved 5 different concentration pulses at 50 ppb of ozone, followed by clean air including regular short heat pulses, which is shown in the middle of the figure. 3 different drift source setups were studied. The blue curve only shows drift due to slow recovery of the sensor. The red curve shows slow recovery in addition to ozone oxidation, and the green curve shows slow recovery combined with secondary layer adsorption. The sensor signal itself has a similar dynamic, or has similar dynamics as real measurements, with a convex adsorption signal and a concave desorption shape. It can also be seen that the blue and green curves show a strong downwards drift as expected, and that the green signal drift exceeds the blue one due to secondary layer adsorption as an additional effect. On the other hand, the red curve only slightly drifts downwards, since the upwards drift due to ozone oxidation slows down the downwards drift due to slow recovery. So summed up, the model follows the physical behavior of the microscopic effects that we would expect. In the second experiment, we determined the model parameters heuristically by a longer concentration profile with different graphene functionalizations, and let it then simulate another concentration profile with different concentration values and compared it to the experimental data. In the first row, you can see the gas concentrations throughout the measurements, where the gray line represents the ozone concentrations, and the black line describes the NO2 concentrations. And in the second row, the real sensor output of the 3 different graphene materials is shown. The third row shows the simulation data generated by the model according to the input concentrations, using slow recovery as the drift source. The general dynamics are replicated quite well by the model. The sensitivity to NO2 was slightly underestimated, however, which might be improved by choosing some parameters in a more analytical way. But summed up, the drift behavior itself also matches the real sensor drift quite well, which is a positive result. So, as a conclusion, it was shown that the model is able to properly simulate the dynamical drift behavior of the graphene-based gas sensor signals, especially in the case of ozone. Moreover, due to its flexibility, the microscopic model can be used to study various different drift effects. And as an outlook, the model could be further improved by choosing the parameters in a more analytical way and by implementing additional effects related to drift that might influence the sensor signal additionally in general. Thanks for your attention.